Diamonds are not rare. Every year, more than 100 million carats come out of the ground. Warehouses hold them by the ton. Entire economies are built to control how many reach the market. Not because there are too few, but because there are too many, and someone decided that scarcity sells better than truth. Somewhere else on Earth, 10 other stones tell a different story. One exists because a single mountain in Utah happened to leak fluorine gas at exactly the right temperature. One was mistaken for something ordinary and sat unnoticed for years. And one, the last stone on this list, comes from a mine so close to empty that within a human lifetime, it may simply stop existing at all. So here's the question worth asking before any of that. What actually makes a gemstone rare? How little of it exists in the ground, or how badly the world has been convinced to want it? 10 stones. One answer, starting with a mineral that cannot decide what color it wants to be. Number 10, Alexandrite. A diamond looks the same in every light. Morning sun, studio spotlight, the glow of a phone screen. It barely matters. The stone offers no secrets, no variation, nothing left to discover after the first glance. Alexandrite refuses that kind of simplicity entirely. Step outside at noon and the stone burns a deep forest green, cool, almost aquatic, the color of light filtering through dense summer leaves. Step under an incandescent bulb that same evening, and the identical stone turns red, sometimes a deep raspberry, sometimes closer to garnet. Nothing about the crystal itself has changed. Only the light source has. Gemologists call this the Alexandrite effect, a shift so complete and so convincing that early Russian miners in the Ural Mountains reportedly believed they had stumbled onto two entirely different minerals. That discovery happened in 1830, inside a mine cut for emerald. Whoever pulled the first crystals from that rock had no reason to expect a color-changing stone hiding among green beryl. The find was named for the young Tsar Alexander II, and it arrived at a moment when Russia's imperial colors, red and green, happened to be the exact two colors the stone performed on command. That kind of coincidence does not sell itself on charm for very long. It has survived nearly 2 centuries in the gem trade because the phenomenon underneath it is real, repeatable, and genuinely uncommon in nature. Here is where the comparison to diamond becomes uncomfortable. For diamond, fine Alexandrite, particularly from historic Russian material, commands prices per carat that rival, and in the strongest color change specimens, exceed a comparably sized diamond of excellent clarity. Modern deposits in Sri Lanka, Brazil, and parts of East Africa keep the stone in circulation today, but crystals showing a sharp, high-contrast shift from green to red remain genuinely difficult to source above a carat or two. Serious collectors rarely chase Alexandrite for its size. They chase it for the exact instant a stone crosses from one light source into another and performs live in front of them. That performance is the first clue in a much larger pattern running through everything ahead. Alexandrite exists because a very specific geological accident, chromium present in exactly the right concentration, locked inside exactly the right crystal structure, happens to occur in only a small handful of locations on Earth. And yet, measured against what comes next, Alexandrite is one of the more forgiving rarities on this list. What follows pushes that same accident so much further that before long, Alexandrite will start to look almost common. Number 9, Padparadscha sapphire. Ask a gem dealer to describe the color of a Padparadscha sapphire, and most will hesitate before answering. Not pink, not orange. Something suspended between the two, the exact color of a lotus blossom at sunset, according to the Sinhalese word the stone borrows its name from. That hesitation is not poetic exaggeration. It is the reason this sapphire commands prices that regularly outpace rubies of comparable size and clarity, and occasionally outpace diamonds entirely. Sapphire and ruby belong to the same mineral family, corundum, separated only by which trace elements infiltrate the crystal as it forms. Chromium produces red and creates ruby. Iron and titanium produce blue and create the sapphire most people picture. Padparadscha requires something far less cooperative, chromium and iron present together, in a narrow specific ratio, without either element overwhelming the other. Push the balance slightly toward chromium, and the stone drifts into pink. Push it toward iron, and orange takes over. The true Padparadscha window is narrow enough that nature rarely lands inside it, and when it does, the result rarely survives large or clean. Historic material from Sri Lanka's gem gravels remains the benchmark the trade still measures every new find against, though Madagascar has produced fine examples in recent decades. Either way, size works against the stone. Padparadscha, above 3 or 4 carats with strong, even natural color, is scarce enough that major auction houses treat a fine specimen as a headline lot, rather than a routine sale. And heat treatment, common and largely accepted in the broader sapphire trade, drops an untreated Padparadscha's value sharply the moment it is detected, because the untouched color is precisely what collectors are paying for. This is where the diamond comparison sharpens further. A diamond's rarity is, in large part, a function of controlled supply, how much a handful of major producers choose to release in a given year. Padparadscha's rarity has no such lever. No mining company can simply decide to produce more of a color that depends on a geological coincidence occurring inside a single crystal, at a single moment, under conditions no one can replicate on demand. The world either finds one or it does not. That distinction, scarcity by nature versus scarcity by decision, is the thread this entire list is quietly pulling on. Padparadscha sits early in the sequence, not because its rarity is modest, but because what follows depends on an even narrower accident of chemistry. Elements not just balanced correctly, but barely existing in nature at all. Number 8. Paraiba tourmaline. Tourmaline as a species is not rare. It comes in nearly every color the eye can register, mined across a dozen countries, sold by the kilogram in some markets. Paraiba tourmaline breaks that pattern so completely that gemologists initially refused to believe it belonged to the same mineral family at all. The color is the reason. Not blue, not green, but an electric, almost radioactive blue-green that seems to generate its own light rather than reflect it. Most colored gemstones owe their hue to iron, chromium, or vanadium, familiar coloring agents that show up across dozens of mineral species. Paraiba tourmaline owes its color to copper, an element that almost never enters a tourmaline crystal in nature. When it does, and pairs with trace manganese in exactly the right proportion, the result is a saturation so intense that early buyers assumed the stones had been treated or artificially enhanced. They had not. The discovery itself reads like a prospector's fable rather than a geology report. In the late 1980s, a Brazilian miner named Heitor Dimas Barbosa spent years digging into the hills of Paraiba State, convinced something extraordinary lay beneath, long after his backers had lost patience. What he eventually pulled from the ground redefined what a tourmaline could look like, and immediately created a market willing to pay prices that had never before applied to the species. Related copper-bearing material later surfaced in Mozambique and Nigeria, extending the color's reach across continents even as debate continues in the trade over whether African material should carry the same name. Here is where diamond once again comes up short. A diamond's value scales predictably with size, clarity, and cut, a known formula, refined over more than a century of grading standards. Fine Paraiba tourmaline answers to no such formula. Per carat prices for the finest neon material have, at auction, exceeded those of comparable fine sapphire and rival top-color emerald, driven almost entirely by a copper concentration that geology places in exactly one narrow set of conditions on Earth. Copper is the operative word here, because it marks the first real turn in this list. Everything up to this point has been rare, because an element arrived in unusual concentration in an otherwise common mineral. What comes next abandons common minerals altogether, species so specific, so narrowly defined, that most working jewelers will go an entire career without holding one. Number 7. Musgravite. For nearly 3 decades after its discovery, Musgravite existed almost entirely on paper. Geologists identified it in 1967 in the Musgrave Ranges of South Australia, from a specimen too small and too flawed to ever be cut as a gem. It sat in mineralogical literature as a curiosity, a confirmed species with no known jewelry-grade material anywhere on Earth. That is a very different kind of rarity from anything on this list so far. Alexandrite, Padparadscha, and Paraiba tourmaline are difficult to find in fine quality. For most of its history, Musgravite was difficult to find at all. The turn came slowly and almost by accident. Musgravite belongs to the same narrow mineral family as Taaffeite, and for years, dealers examining parcels of what they believed to be ordinary spinel occasionally sent stones for testing out of routine caution. A small number came back identified as Musgravite instead, gem-quality material that had been sitting, misclassified, in jewelry inventories for years. Madagascar and Sri Lanka have since produced additional specimens, but the total number of faceted, gem-quality Musgravite stones known to exist worldwide is still commonly estimated in the dozens, not the hundreds. That scarcity shows in the price. Fine Musgravite has traded at auction and in private sale for figures exceeding $35,000 per carat, a number that holds up against only the rarest colored diamonds, and does so without any of the marketing infrastructure that supports the diamond trade. There is no Musgravite advertising campaign, no cultural tradition built around it, no engagement ring standard driving demand. The price exists purely because almost nothing to sell exists at all. This is where the comparison to diamonds stops being uncomfortable and becomes almost irrelevant. A diamond's scarcity, whatever its degree, still supports an entire global industry. Mines, cutting houses, certification labs, retail networks built around a steady, if controlled, supply. Musgravite supports none of that. There is not enough material in existence to build an industry around. What exists by accident, in parcels once mistaken for something else entirely. That distinction, a mineral so rare it was misidentified for decades simply because no one expected to find it, marks a shift in this list. Musgravite is not merely uncommon. It is a species the trade itself was not prepared to recognize. And what comes next takes that same problem further still. Gemstones so scarce that entire countries can claim, credibly, to be the only source on the planet. Number 6. Red beryl. Emerald and aquamarine both belong to the beryl family, and both owe their fame to how often nature produces fine examples of each. Red beryl belongs to the same family and owes its fame to the opposite fact. Nature almost never produces it at all. The color comes from manganese, not the chromium or iron that colors its beryl relatives. A substitution rare enough on its own. But color is not what makes red beryl exceptional. Location is. Gem-quality red beryl has been confirmed in commercial quantity in exactly one place on Earth. The Wah-Wah Mountains of southwestern Utah, where the crystal forms only under a narrow set of volcanic conditions involving fluorine-rich gas moving through rhyolite rock at precisely the right temperature. A smaller, largely non-commercial occurrence exists in New Mexico. Beyond that, the geological recipe simply has not repeated itself anywhere else that has been found. The scale of the scarcity is easier to grasp in a single comparison. For roughly every 150,000 diamonds pulled from the ground worldwide, industry estimates suggest only one red beryl crystal of any quality emerges from Utah's volcanic terrain, and the overwhelming majority of those crystals are too small, too included, or too poorly formed to ever be faceted. Fine red beryl above 1 carat is considered exceptional. Above 2 carats, specimens become the kind of stone a collector may wait a working lifetime to encounter. Then there is the matter of the mine itself. The primary commercial source, the Ruby Violet claims, has changed hands and operating status over the decades, with periods of closure that remove new material from the market entirely for years at a stretch. Diamond supply, whatever its scarcity, can still be expanded. New deposits explored, new mines opened, production adjusted to meet demand. Red beryl supply cannot. It depends on one region of Utah continuing to yield material from a geological process that, as far as anyone has confirmed, does not occur anywhere else on the planet. That single source dependency is the detail worth sitting with. A diamond's rarity at its core is a business decision. How much a handful of producers choose to release. Red beryl's rarity is a geographic fact with no lever anyone can pull to change it. And this list is only beginning to explore what happens when that single source problem becomes even more extreme. Stones tied not to one mountain range, but to a handful of individual crystals, period, anywhere on Earth. Number 5. Serendibite. For most of the 20th century, Serendibite existed in gemological literature the way a myth exists in folklore. Described, referenced, occasionally argued over, but almost never seen. The mineral was first identified in 1902 in Sri Lanka and took its name from Serendib, the island's old Persian and Arabic name, the same root that gave English the word serendipity. For decades, that etymology felt like the entire point. Finding Serendibite at all was treated as a stroke of luck bordering on fiction. The reason was simple and unforgiving. Early specimens were opaque or so deeply included that faceting them into a transparent gem was effectively impossible. For years, the total number of cuttable Serendibite crystals known to exist worldwide could be counted on two hands, and gem dealers who had spent entire careers handling ruby, sapphire, and emerald had never once held one. A single clean, faceted Serendibite became less a gemstone in the ordinary sense and more a kind of proof, evidence that the mineral described in a 1902 paper actually existed outside of it. That changed only slightly in recent decades, with additional finds in Myanmar and Madagascar adding a small number of new specimens to the world's supply. Slightly is the operative word. Serendibite remains one of the only gem species where a private collection holding even a single well-formed, transparent stone is considered a genuine achievement, not a starting point. The color runs from pale yellow through deep, almost inky blue, occasionally shifting toward black, but color has never been the draw. Existence itself has been. This is where diamond, for a moment, stops being a useful comparison at all. Diamond scarcity operates on a scale of millions of carats, controlled and released deliberately. Serendibite scarcity operates on a scale of individual stones, tracked almost by name, where a new find is significant enough to be reported the way a rare fossil discovery might be. There is no market mechanism to expand supply, no mining operation dedicated to the mineral, no predictable channel through which more will ever reliably arrive. What Serendibite reveals, more than any stone so far, is how thin the line runs between a gemstone and a geological accident that simply happened to be beautiful enough to keep. The countdown now turns towards stones defined by exactly that same accident, mineral species so narrowly confined to a single environment on Earth that their entire global supply can be traced, quite literally, back to one mountainside. Number 4, Grandidierite. Turn a fine Grandidierite between your fingers, and it performs a trick most gemstones cannot. Held one way, it reads deep blue-green, close to the saturated tone prized in fine Paraiba tourmaline. Rotate it, and the color shifts toward a pale, almost colorless green. Rotate it again, and a third tone emerges entirely. A phenomenon called trichroism, the ability to display 3 distinct colors depending on the angle of view. Alexandrite changes color with the light source. Grandidierite changes color with nothing but the angle of the stone itself. The mineral was first described in 1902 in southern Madagascar and named for the French explorer and naturalist Alfred Grandidier, who had spent decades documenting the island's natural history. For most of the 20th century, Grandidierite remained a mineralogical curiosity rather than a gemstone. Specimens existed, but almost none were transparent enough or large enough to be faceted. A collector could own a piece of Grandidierite rock. Owning a clean, cuttable crystal was another matter entirely. That has shifted only modestly in recent decades. A small number of additional deposits have been identified, including limited material from Sri Lanka, but Madagascar remains overwhelmingly the source the trade relies on. And even there, gem-quality rough sufficient to yield a transparent, well-colored stone above a carat or two is scarce enough that most working gemologists will handle only a handful of specimens across an entire career. Fine, transparent Grandidierite above 5 carats is considered exceptional enough to draw attention at any major gem show. The price reflects that ceiling. Top quality material has traded in the range of $8,000 to $20,000 per carat, and stones above 2 carats rarely surface at auction at all. Not because demand is weak, but because supply above that size essentially does not exist. A diamond buyer choosing between a larger stone and a smaller one is making a decision about budget. A Grandidierite buyer choosing a stone above 2 carats is often not choosing at all. The market simply has not offered one. What Grandidierite adds to this list is not just rarity, but a reminder of how recently some of these gemstones crossed from mineralogical footnote into the trade at all. A stone identified in 1902 that only became reliably cuttable within living memory says something diamond, mined and cut for centuries, cannot claim that somewhere on Earth, gemstones this rare are still being figured out in real time. What comes next pushes that idea further still. A mineral once mistaken for something else entirely, hiding in plain sight inside collections for decades before anyone realized what it actually was. Number 3. Taaffeite. In 1945, a Dublin gemologist named Richard Taaffeite sat examining a small parcel of cut stones he had purchased as ordinary spinel, an unremarkable, if pleasant addition to a working collection. One stone in that parcel behaved differently under his instruments. It doubly refracted light in a way spinel, a single refractive mineral, simply cannot. Taaffeite had not bought a parcel of spinel at all. Buried among them was a mineral no one had ever formally identified, and it had already been cut, polished, and sold as something else by dealers who never noticed the difference. That origin story is not incidental to why Taaffeite matters. It is the entire point. This is a gemstone that existed in jewelry, in trade, in collections, for an unknown stretch of time before anyone realized it was not what it appeared to be. Spinel and Taaffeite share enough visual similarity, soft purples, pale mauves, occasional reds, that the two were, and occasionally still are, confused by eye alone. The difference only reveals itself under refractometer testing, a step routine dealers rarely apply to stones they already believe they understand. Since Taaffeite's discovery, additional material has surfaced in Sri Lanka, Tanzania, and China, but the total known supply remains staggeringly small. Industry estimates place Taaffeite at over 1 million times rarer than diamond by weight of material ever recovered, a figure that sounds implausible until measured against how few confirmed specimens exist in gemological records at all. Most cut Taaffeite weighs under a single carat. Stones as any real size are treated less as inventory and more as documented rarities, tracked individually rather than by weight. The price reflects a mineral still working out its place in the market. Standard Taaffeite trades in the range of $2,000 to $4,000 per carat, but exceptional color and clarity has pushed top specimens toward $35,000, a spread wide enough to suggest a trade still calibrating value for something it rarely encounters. Here, the diamond comparison collapses in an unexpected direction. Diamond's entire grading system exists because there is enough material and enough transaction history to standardize it. Taaffeite has neither. Every fine specimen is, in a real sense, its own case study. And that raises an uncomfortable question the countdown has been circling since Alexandrite. If a mineral this rare hid inside jewelry collections for years, unnoticed, how many more accidents like it remain uncatalogued right now? Sitting in a drawer, a museum tray, or a parcel of stone someone has already mistaken for something ordinary. The next entry answers that question in the most extreme way this list has to offer. Number 2, Painite. For most of the 20th century, one gemstone held a distinction that no marketing department could have invented. The official record for rarest gemstone on Earth, confirmed by Guinness World Records. Not the most expensive, not the most sought after, the rarest, full stop. That title belonged to Painite. The stone was first identified in the early 1950s, when British mineralogist Arthur C. E. Payne sent a handful of unusual reddish-brown crystals from Myanmar for analysis, believing them to be a known species. They were not. For decades afterward, the world's entire known supply of Painite consisted of exactly 2 crystals, not 2 carats, not 2 parcels, 2 individual stones, both housed in museum collections, both studied more than they were ever seen. A working gemologist could spend an entire career without encountering Painite outside a textbook photograph. That changed modestly in the early 2000s, when new deposits near Mogok, Myanmar's historic gem mining region, produced additional specimens. The total known count rose from 2 into the hundreds, a dramatic increase in relative terms, and still a number small enough that most fine jewelry stores worldwide will never carry a single piece. Painite's color runs from a deep brownish red to orange, occasionally shifting toward pink under different lighting, and the crystal's hardness, around 8 on the Mohs scale, makes it durable enough for jewelry if any collector were willing to wear a stone this scarce rather than lock it away. Even now, with supply modestly improved, gem-quality painite suitable for fast setting remains a fraction of the material found. Most crystals are too small, too opaque, or too fractured to yield a clean stone above a carat. A well-formed transparent painite above 2 carats is rare enough that its sale is typically reported within the trade, the way a significant fossil find might be reported in paleontology. As news, not inventory. Diamonds' record-setting stones make headlines for their size, their color, their auction price. Painite made headlines simply for existing in more than one place at once. That is a different category of rarity entirely. One where the achievement is not owning the finest example, but owning any example at all. For over half a century, painite stood at the absolute edge of what geology was known to produce. Then, in 2015, in the same country that gave the world painite decades earlier, a discovery surfaced that made even painite's 2-crystal origin story look almost generous by comparison. A mineral so scarce that, as this list closes, science still recognizes only one confirmed specimen on the entire planet. Number 1. Benitoite. Turn off every light in the room, and most gemstones simply disappear into darkness. Benitoite does the opposite. Under ultraviolet light, the stone erupts into an electric, almost radioactive blue. Brighter, sharper, more saturated than the stone appears in ordinary daylight. Gemologists still debate exactly why the fluorescence reads so intensely, even among specialists who study it. Nothing about that reaction can be manufactured. It is simply what the crystal does. The mineral was first described in 1907 near the headwaters of the San Benito River in San Benito County, California. The discovery that gave the stone its name and eventually made it California's official state gemstone in 1985. From the beginning, Benitoite behaved unlike almost anything else in the gem world. Gem-quality material has been confirmed, in any real commercial quantity, at exactly one location on the planet. Small occurrences have surfaced elsewhere, in trace, non-gem quality, but the source that mattered, the one mine that supplied nearly every faceted Benitoite ever sold, sits in that same stretch of California hillside. That mine has been worked, on and off, for more than a century, and the geology behind it does not appear to repeat. Production has slowed dramatically in recent decades, not because demand fell, but because the deposit itself is approaching exhaustion, a resource with a visible, calculable end, rather than a market simply choosing to hold material back. Most faceted Benitoite weighs under a carat. A stone above 2 carats is considered a serious rarity, and the largest gem-quality crystal ever recovered weighed just over 15 carats, rough. This is where the diamond comparison finally closes. A diamond mine exhausted can be replaced. Geologists locate new kimberlite pipes, new deposits, new sources, somewhere else on Earth. Benitoite offers no such second chance. The total supply that will ever exist is, for all practical purposes, already determined by what one hillside in California has given up so far, and what little remains for it to give. That is the answer this entire countdown has been building toward. Diamonds are rare because their supply is managed. These 10 stones are rare because their supply was never a choice at all. Geology decided once, under conditions that will not occur again, and what exists now is close to all that ever will. 10 stones, one mountain in Utah, leaking fluorine gas at exactly the right moment. One crystal, mistaken for something ordinary, sitting unnoticed for years before anyone looked closely enough. And one hillside in California, giving up the last of what it has left to give. None of that was a decision. No boardroom set a quota. No mine manager chose to hold supply back. Geology simply happened once, under conditions that will not happen the same way twice. So the question from the beginning has its answer. A diamond is rare because someone decided it should be. These 10 stones are rare because no one was ever asked. That is the difference worth remembering the next time rare is the word on the label. If a mineral can hide inside a jewelry collection for years before anyone notices what it really is, there is no telling what else is still waiting to be found. This is Tops, where every stone tells a story. Subscribe and stay for the next one.